Okay, welcome back to the afternoon session. Delighted to have Gualdani, who will be talking about, I'll read your title, regularity estimates for the Landau equation near equilibrium.
Thank you very much. Thank you for the introduction. First, thank you, the organizers, Dallas, Sam, Laszlo, for the very kind invitation. It's an honor to be here. Happy birthday, Alexis. Thank you. And so today I will talk about very recent results on the Landau equation near equilibrium. So we will see what this means. So the Landau equation, it was introduced by Lev Landau in 1936 as a model to describe collision in plasmas. And the more general formulation that the equation has is this one. Then we have at the top. So it's a kinetic equation. So the unknown, this function f, is statistical quantities, probability density, that describes, as I said, the probability of finding particles at position x with velocity v and time t. So the left-hand side of the equation describes the transport in the system. The left-hand side, the right-hand side describes the collision. And the Landau collision operator has this form over here. So it's the divergence with respect to v of the difference of two terms. Then we will see in a little bit by what they mean. It's an operator that, as you see, only acts in the velocity variable. So collisions are localized with respect to space and time. And it's a nonlinear, as we see, a second order, and I put in quotation mark elliptic operator. We will see this why that is. So just a little bit of history. It was derived from the Boltzmann equation by Lev Landau to describe collisions in plasma. For those in this particular setting, the Boltzmann model becomes ill-posed. So this was known. So he proposed this new model in 1936, and 20 years later, the same equation was derived from a completely different point of view as a nonlinear Fokker-Planck operator. And this derivation, which is actually quite nice to follow, can be found in the monograph course of theoretical physics by Lifshitz and Pytajewski. So, and after it appeared, so it's actually, so can be interpreted as the first approximation in the mean field regime to the Vlasov equation, okay, just to take into account collisions in the particle. And it's also somehow a simplification of the Balescu-Lenard collision integral, which is much more complicated. And it's definitely one of the most important models used to model collision plasma. So I will simplify a little bit the equation and consider the what's it called, the homogeneous setting. So by that I mean we assume that the distribution of the particles is independent on the spatial variable x. So f is a function which is constant in x, and now we only concentrate what is happening in the velocity and time. So in this framework, then the Landau equation becomes an elliptic equation. So now if you see that, maybe it's not so clear. So let me do a simple computation. So it's a divergence form. So, and what happened is that, assuming that the function f is as smooth as we wish. So what I will do is I can do all the manipulation that I'm doing now. So since the integral is in the velocity variable in dw, for example, we can take in the first term, we can take the gradient with respect to v, we can take it out of the integral. So we can rewrite it as the divergence of a matrix A of f, gradient f, this is in v, and this matrix A is what remains. So will be the integral in R3 of the projection matrix over the kernel, V minus W, and then we have, so it's an average, right, of F. And I do the same manipulation now in the second term. I take the F of V outside, and then we have the divergence of this matrix A of F, okay? And it is kind of direct to see that actually if we take the divergence of this matrix A of F, this is exactly the gradient of a scalar function, then I denote it by little a, with the property, and the scalar function has the property that the Laplacian of A is negative F, is the risk potential. So now you know exactly where I'm aiming at, because if we now distribute the divergence to the two terms, the first term then we get is, okay, the elliptic one. So we will have, if I here, so when we apply the divergence to the gradient, we will have the trace of the diffusion matrix, K of F, H and F. Now, when we apply the divergence to this one, we'll cancel out with when we apply divergence this one, and then the only term that remains is F Laplacian little a, which is F square. Right? So here is the maybe 3 different formulations which are equivalent if the F is a smooth function. So, and different approaches, different type of results use either the first one, the integral formulation, say, or the second one, the divergence formulation, or the third one, the divergence-free formulation. Okay, so the most important facts, and maybe the most important facts about what I will talk about later, about this equation. As for Boltzmann, there is an equilibrium state, which is the Gaussian function, e to the minus b square. There are 3 conserved quantities, where the mass, the momentum, and the energy. And that is a very easy things to see that there is conserved. Not if you use this one, not if you use that one, but if you use the integral formulation. The computation is very, very easy. And the entropy, the Boltzmann entropy decays, exactly as in Boltzmann. So the 3 characteristic things are the same. Okay. Now, I said before, it's an elliptic operator. Why? Because this coefficient, this diffusion coefficient A, is bounded from below by a polynomial. So even if it's an average in F, okay, there is actually a uniform bound from below that degenerates when V is large, but still, right? It's a good bound, okay? And it's actually sharp if F is the Maxwellian. So cannot be better than that, okay? So the most important question is if solutions to this equation, the Landau equation, stay bounded or not. The culprit, you understood what it is the quadratic nonlinearity, right? So we can have appearance of blow up either in finite time, in finite time, or at infinity, but not at infinity. This we know already. So what do we know about this problem? So existence of weak solutions, this is known since a long time. Started with very weak solutions, so renormalized solutions like for Boltzmann, but for Landau they were called H solutions. Very weak, right? Later on, actually 8 years ago, De Villette showed that those weak solutions, those very weak solutions are not so weak. They're classically weak. They satisfy a standard weak formulation. Now, a lot is known about long-time asymptotics. This is kind of clear what is happening in L1 norm or in the entropy norm. Any solution converges towards the equilibrium. Okay. And there are many works on that, and the names are, this list is not exhaustive at all. So it's just maybe the first ones or the last ones, and many people have worked in different, with different questions, different settings, and the literature is really vast. So global well-posedness to equilibrium. This is also kind of understood. This is what I will actually talk about today. It's a recent result about global well-posedness. Well, initial data are in LP with P small. Okay, this was an open question. Then about uniqueness. Well, uniqueness is another kind of a research program that has a lot of open questions. So especially known because when initial data are smooth, we know there is a unique solution. So when initial data are smooth and solutions are smooth, then they are unique. But what we don't know if when initial data are not smooth. This is a completely open question. And it seems kind of hard. Maybe it's not even true. Then there is uniqueness. So we really don't know. Okay, so if you would like to take a look at what is in the literature and so regularity, since we cannot rule out, we cannot either show global well-posedness, not rule out blow-up. So what about regularity? Well, there are three types of somehow research programs. So the first one is conditional regularity. So what I mean by that is assuming that I know a little bit more, then I assume a little bit more. I don't know if that is true, but assume then I know a little bit more. Can I say a lot more? No? And so, and now, for example, what is well understood is that actually to show that we are there is no blow up is not necessary to show that the solution is bounded. Actually, it's enough to show that we are a little bit integrable. How integrable? So if F is uniformly in time in some LP, so in 3 dimensions is P greater than 3/2, okay, then the function is bounded for all time. Okay, so this is known, and now we have understood how that. And there are 2 proofs actually. The first one appeared in 2016, I think, by 2016 by Luis Silvestre, and the proof was based on a Krylov-Sofanov method. So starting from the non-divergence form of the equation, then a second proof appeared by myself and then Sorguyen in 2019 using energy method, started from the divergence formulation. And then there are many more also for the inhomogeneous, so going into the real kinetic formulation. So the second line of research in this field is the partial regularity, and this one I will not say more because I think the next talk will be on it. So right, so I will leave you like that, and then the last one is actually a result, a very sharp result that De Villette and Zhang proved maybe 2 years ago. And we call it eventual regularity. So they showed that if there is a blow up, this blow up will happen soon, in finite time. Eventually, whatever happens, whatever singularity, pathology that can happen, eventually the solution will be smooth and will live forever. Okay, so. I don't know. I read it here.
Partial regularity.
It can be a consequence of it.
Okay. Yeah, because if you're small enough.
Yeah.
That's right.
But it first appeared there, right?
Big interval of time would always have this condition.
It first appeared there because their paper appeared in 2020. So this is a 2000.
It's not neurological.
No, De Villette and Zhang paper appeared in 2020. They have actually kind of several results in a new monotonicity formula, a new proof of global local well-posedness, and then they show that this eventual regularity result, that if you wait a little bit, that things will become smooth again and will live forever. And of course, this be a consequence of also, because it all matches, right? It all makes sense, has to. Okay, so and today, as a second result, I will also do a little comment about the strength of the diffusion. Okay, so it's more a reflection or maybe a new point of view. I don't know. We will see. And then, since we cannot show global well-posedness straight, can we rule out blow-up? So this is maybe other type of questions and one can look at. And so the answer is yes. For example, we can rule out type blow-1, self-similar type blow-1. This is actually very easy to show, but there are, of course, many more types. So if maybe you would like to take a look at what can be done, things get a little bit more complicated, but nevertheless. Okay. The conjecture, if solutions for general initial data smooth, of course, this is still open. So what are the obstacles? At least in my opinion, the main obstacles for this problem. So first, there is no comparison principle, okay? Because, of the non-locality of the coefficient, especially of the diffusion coefficient. The second one is that the only energy function that we know that is bounded actually is the Boltzmann entropy, modulus some minor modification, but morally is the F log F. It's the only thing that we know that is conserved in time, actually decays. And the third one, which maybe it's the hardest one, is the fact that the diffusion and the reaction are balanced. So this, as I wrote here, this can be seen in different ways. So by a scaling. If we do the scaling, the F square scale exactly like the A Laplacian F. So the diffusion doesn't scale like Laplacian. The diffusion scales of order 1. Okay, it's because the A scales like 1 over Laplacian. So they are exactly balanced. Okay. Another way how to see that is via a new weighted Poincare inequality that was introduced 10 years ago by Grassmann, Krieger, and Strain, and said exactly this. Something like this happens if we do energy estimates, right? So that the LP plus 1 norm is basically equivalent to the diffusion term, and those two blocks, they balance exactly at the equilibrium. No? At the equilibrium, we have exactly the balance. Okay, so the fact that we cannot say which term takes over in which regimes is somehow maybe one of the biggest obstacles. So the theorem of today, so it's a joint work with William Goldin. He's a graduate student at UT Austin, co-advised by Alexis and myself. And then Emily Loher, as graduate student, also here from Cambridge. Okay, so the theorem says the following. So we have, let's consider an initial datum which has a bounded entropy and some moments. We have a degenerate diffusion, so obviously the moments, they come into play at some point. This Lebesgue bracket just denotes smoothing version of the absolute value. Okay, so think about basically the absolute value. So we have initial data, some moment bounded, the entropy, the moments, and then they are close in some LP spaces, close to the Maxwellian, and P is strictly bigger, but arbitrarily close to 3/2. Okay. Then for such initial data, the Landau equation is globally well posed. And moreover, there is a regularization estimate that so from L1 to from LP to L infinity, and the decay rate is 1/T to the gamma, and gamma is all up to a correction because of the moments is the same rate as the heat equation. Okay, so this result shows actually three things. First, so unconditional regularization estimates for close to equilibrium regime in LP norm, but those regularization estimates are strong enough to give us global well-posedness. So a comment on the P greater than 3/2. Well, our method relies on energy estimates, and they hold when the diffusion dominates the reaction. And that is true for subcritical norms. And LP greater than 3/2, those are subcritical for Landau up till now. Maybe can change, but until now, that is the threshold. It's not by chance that this one is the same as that one, right? It's kind of the same concept somehow. So when we are in subcritical norm, this diffusion here becomes morally like a Laplacian, right? And so this is why you get also the regularization estimate that is the one of the heat equation. Okay, so before I go into the proof, I will give you a very simple argument. So assume that now we are not, this is the identity matrix, okay? So this is one, okay? And so then it's basically the Keller-Segal equation, right, in 3 dimensions. So what I do is I'm going to do L2 estimate. I'm going to multiply by U, integrate by parts. So the first is the first term that we get on the right-hand side is the diffusion, so the coercive term. And then we will have an L3 norm popping up from the reaction. So I'm going to do interpolation. I mean, I want to recover an H1 norm from that one. So L6, L3 the square norm of in L6, I'm going to bound with Sobolev and then I recover the gradient square. And then I'm going to interpolate the L3 between L2 and L1 because on the left-hand side I have L2. L1 is a constant because we have an equation in divergence form. So now if we take the gradient square as common factor, you see that if the initial data have smaller than a certain constant L2 norm, then the L2 norm will stay bounded forever, right? Because I have no idea how this will grow, but if initially this is positive, the L2 norm will keep decaying and stay bounded forever, okay? So what is the reality then? Okay, so now my reality is that my U will be the difference between the equilibrium and F. And U satisfies this nonlinear, obviously, very similar to the original equation, with some extra terms that come from the Maxwellian, but those are linear. Okay, so and I mimic what I've shown you before, not with L2 but with LP. Okay, and I have to take into account these extra terms. Obviously, we shouldn't expect that this is uniformly decaying. It might not even be true, right? As the example that I showed you earlier. But nevertheless, so I'm going to do similar tricks as before, and what we get is that, well, for a short time, okay, if I start small, I'm actually, I keep the smallness. Okay, I keep the smallness, and actually I have something more than is also small. I have some coercive term, right? Some gradient that is also small. Okay, so now I know quantitatively, I start small, I keep small for this time interval, and I do the regularization estimate. So I can get an L infinity bound, okay, that of course will have a negative coefficient and will deteriorate when t goes to 0. Because I didn't start at infinity, I started LP, right? But at some point in this time interval, my L infinity estimate is small. This is important. Okay, my L infinity estimate is small, and I can do more. I can also show them some higher regularity, so some Sobolev norms are not only finite, but small, okay? Why do I want that? I'm still in short time, but now I take all the literature that we have available. And what we know is that if we take the Landau equation with small initial data, small means near equilibrium, right? So small and smooth, then we have global existence. Okay, so, and I start with something that is not smooth, but I can show that after a little time, I'm small and smooth. Okay, so if I take now this value as my initial data, I have a global solution. But I have also uniqueness. No, this is, for example, in L1 time, L infinity in space. So I have also uniqueness. And therefore, I can match my short time solution with the global one that I build after a certain time. And so I have for free, basically, right? Global in time solution. So we only had to work for a little bit, and then we use the existent result to latch to infinity, basically. Okay. And so those some comments. So it is a result near equilibrium, but the method is non-linear. So we didn't linearize, we didn't consider linear operator and study the spectrum, anything like that. I think, well, the aim was we were more ambitious, but yeah, the equilibrium is what we can do until now. And this is, I think, the main reason why we don't need to touch the momentum. Usually, in this type of near equilibrium methods, there is a linear part and a nonlinear part, and then usually we build in a spectral gap, push the continuous spectrum on the side, and to do that one, you need moments. L2 or whatever, infinity, but we are not doing that. I'm not looking at the linearized operator, anything. So I just need some small quantity that I can push over. And the short time estimate, the short time regularization estimate is like the one of the heat equation. And as I said before, the restriction, P greater than 3/2, is needed because it bounds it shows that the diffusion dominates basically to the reaction. Should the result be true for smaller p? Yeah, I think so, but with different methods, not with this. I think for that one we might require a new idea. But okay, so this is something that is still open, and we don't know how to do up to today. So the next one is the next result that I wanted to present is more like as I said before, a reflection. So regarding the diffusion, as I said at the beginning, so so this one here, so the diffusion coefficient is something that can be unbounded, right? Because if f doesn't have the proper regularity, then the A of f can be very small, and it's bounded below uniformly by this polynomial. And so in many results, so this bound from below is very convenient. We all rely on that at some point in the paper. So, and is this okay? Because as I said, it's sharp when we are near equilibrium. So, but the question is that, do we lose something if we are not near equilibrium and we rely on that bound? So the interesting thing is that in this line of since some years, there haven't been on the Landau. We don't know anything about global posedness, but we know something about some related models. And interestingly, the sharpest results, so when we can say yes, the solution is globally well posed, is when we do not rely on that lower bound. So let me give you 3 examples. So the first one was the work by Gressman, Krieger, and Strain in 2012. What they said is that, okay, I'm going to basically remove this projection metric from. This is just a projection metric, right? It's bounded between 0 and 1, and so shouldn't play that much of a role. So I'm going to remove this one, and then what they did is that they damp a little bit the reaction, not the power, but they put a small coefficient in front, and they could show that this equation here is globally well posed by using this new weighted estimate. You see, the diffusion is there. Full. I mean, they are not using the lower bound. So the next one was one of my work that appeared 4 years later, where we consider the same equation, but now we remove the damping. And we could show global well-posedness for a solution by abandoning energy estimates and by running a barrier argument for the mass function, also leaving the diffusion as it is. And the third one is, so we consider less singular kernel, and we could actually show that this equation here is also global well posed when gamma is below -2 for a little bit. And how we did it with Hardy inequalities, leaving the diffusion there where it is and not using the lower bound. Okay? So we thought about, is there a way how to quantify how much we lose if we rely on the bound from below? So basically downgrading the Landau diffusion to the Laplacian, right? This happens when we use the lower bound. So now let's consider this problem. This is a joint work with René Cabrera. It's a student, a postdoc at UT Austin. And so let's consider the diffusion problem. Okay, so now I took this out, okay? And what we can show is actually that that operator has a regularization power much stronger than the Laplacian. So if we start with L1 initial data, actually it regularizes instantaneously as it expected, but with a rate T to the 1 plus epsilon, which is much faster than the rate of the heat equation, which is 3/2 in 3 dimensions, or d/2. Right? So the regularization power of the Landau diffusion is much stronger than than the Laplacian. Okay, and the proof, and this epsilon, so we cannot, this epsilon is a positive number, but it's actually as small as one wishes. So there is a type of, how can I say, the enhancement regularization intrinsic in the Landau operator that maybe we don't know how to use it yet. And the proof actually of this result is very easy. It's very easy, and it relies on essentially it's 2 steps. The first step is L1 LP regularization, so we just do LP energy estimate, and if we use the Gressman-Krieger strain inequality, we can bound the LP norm by the P+1 power of the LP+1 norm, and then doing some interpolation, we arrive at this decay, which is already much faster than the one of the heat equation. I don't remember yet exactly how it is, the L1 LP. There is some powers there, so this is already much faster. At this point, we cannot push P to infinity because the constant in front will blow up. So the next step is, okay, I'm going to do the Giorgi argument, LP to L infinity. And if I do that, I get some decay, okay? And if now we combine what we have above with the previous one, the 1 L infinity, we are getting exactly something like that. So that if we start with L1 initial data, the function U will be instantaneously bounded with a decay rate that is morally like 1 over t. And so now maybe it's the question, what do we do with this information? Well, I don't know. Until now, I don't know. I don't know how to use it. And I don't know if it matters that much for what can happen after a certain time. But this is definitely a sign that this operator here is actually very strong, right? And maybe there is a need to show a better bound from below than not just the polynomial, because the polynomial loses a lot, right? It's good near Maxwellian, so if you do not equilibrium, I think maybe this is good enough. But otherwise, maybe we are losing something. And so yeah. So and with this one, I think I'm done. Happy birthday, Alexis. Happy birthday.